So welcome back. This is our next video in our discussion of probability as we move our way into statistics studies later on in the series. We're still doing some of the basics, and if you recall in some of our previous videos, we've been doing some fairly simple calculations with regard to events and sample spaces and figuring out number of outcomes and then some basic probability using equally likely outcomes. In this one, we're going to go a little bit further and start showing you some ways to be able to come up with some of these quantities, these counting methodologies, when it's just not practical to sit there and write out everything in a sample set. If you remember, we did, the example where we rolled a couple of dice and had 36 outcomes and we wrote all of them out. Or we flipped a coin and we had two. What happens when those numbers get too big and start borderline immeasurable? How do we start to handle that information, and come up with those numbers without having to write everything down? And so this is their, if we can get these masteries of these formulas, then we should be good to move forward into bigger and more complex problems. And that's where we're going to kind of start with. So as we start to kind of look at this today, okay, we're going to define an event A here, okay, and then we've got our sample space is still defined as S. If you remember from last time, for equal likely outcomes, we defined that the probability of A, our event A, is the number of ways that A can occur over the number of ways that S can occur. Okay, and it's kind of a percentage, what percent of the events in AS are event A. Okay, and so if we do that, we're going to kind of start to define out our, for the equal likely outcomes case, something known as the product rule. And it basically says that if a set has K elements, and there are N1 choices for the first element and N2 choices for the second element, and so forth and so on, all the way up to, NK elements for the K element, then there are total number of ways in the sample set of just simply being the product of all of those numbers, 12 for the first one, 9 for the second, so forth and so on. Those are the possible sets, or what they call a K-tuple. Okay, and so that's where we're kind of going with this. So now we'll kind of illustrate this here with a quick example, and then I'm going to try to show you some graphical techniques on the way I kind of look at things that help me to visualize how these numbers are working, and you'll start to see that they can get very, very big very, very quickly. Even if your basic setup is just very small numbers of events. So for the first example that we're going to choose to look at, we're going to look at how many ways can we choose 12 plumbers and 9 electricians, from this problem was originally a Rolodex problem to give you some idea of how dated it is. I guess we don't really have Rolodex anymore, but number of cards or number of contact lists or whatever we have on there. How many different ways can I choose a plumber and an electrician from this list? Okay, and so the way that we look at that, the product rule says, okay, well, my N1, if I say plumbers is the first event, that I would have 12 of those, and the electricians would be 9 of those. That would be my second event, that the number of ways that all of the possibilities of combinations of those, if you want, of those. And we got to be careful when we use the word combination. It has some specific meaning, but just the number of ways that we can combine all of those is that the number of sample space is 12 times 9, which would be 108 different ways to choose those. Okay, now again, with a formula, and this is what I kind of warned early on, is that we don't want to just memorize formulas willy-nilly on this. We want to kind of look at graphically, what does that represent? And that will kind of help us be able to derive this. So what I like to do is I like to draw something called a tree diagram for this. And it's basically, I start off, and the way I usually draw these is generally from left to right. Sometimes I go top to bottom, but generally left to right. And you'll see that I start off with my main element. This is my overall encompassing, this is my sample space. So everything that comes off of this is, if you imagine the trunk of a tree and the roots would be over here, this is the starting point. Everything that we do is within the context of S. So if I look at this, if you think about, I'm going to look at, call my first event, the number of ways that I can, the number of ways that I can choose a plumber, and so we've numbered our plumbers 1 through 12 because there are 12 of them. So, I could pull plumber 1, or I could pull number 4, or number 12, or any of the numbers in between. Now, I didn't draw all of them, but I did, but they are there. Okay, and then once I choose one of those, let's say we chose number 1 as the plumber number. Okay, then for every one of those, okay, we go and we look at our event B, which would be our J event, and we'd be choosing our electricians, and there are 9 of those. So for every one of these that we choose for the first event, there are 9 possible choices for it. So I had, for this plumber, I could choose any one of the 9 electricians. For number 2, I could choose any one of those same 9 electricians. Then these all give me unique paths and unique outcomes. So when I come out this far side here, okay, each one of these paths, if you will, becomes a unique outcome within this sample space. Okay, so outcome, number one plumber, number one electrician, that's one outcome. Number one plumber, number two electrician, that's another outcome. And we can start to kind of map these things and look at all these. So you can imagine that if I did this and I repeated this process for all 12 of these, there would be 108 different outcomes when I got all said and done. And how did I get that? Well, for every one of these, there were 9 of these. So 12 of these times 9 of these, there's your product formula. That's where it's coming from. Okay, and for that, we could have sitting here and wrote out all of these, and there's only 108 of them, so I guess it wouldn't take too long to do it. But what are the odds that you miss one? That this is fairly simple. Maybe it's not very likely, but more complex problems, it's possible that you just don't observe or just don't think of a certain particular case that would be in the sample space. The counting will help you. Okay, and so this product rule is a very, very powerful way to look at that. So lots of ways to kind of look at that. So anyway, this would be the actual sample space, but this is the way that I like to visualize things. And I do a lot of stuff off of this because I'll show you how you can use this tree diagram as a tool going forward that will greatly, greatly simplify a lot of our counting endeavors. Okay, all right, now within any probability and statistics problem, we have a couple of topics that are generally a source of confusion because and that is the idea of a permutation or a combination. Okay, now you may have seen this back in a previous math class, high school algebra or something. But there are some very subtle differences that happen with this. So we're going to start off. I'm going to walk you through both of these, and then we'll show you how you can kind of start to use these and put these types of problems together. So we're going to start off with our permutation. Okay, and so the definition of a permutation, there's some criteria that you have to meet. So what we're looking at is when choosing an ordered, and I underline ordered, sequence of k objects from a set of indistinct objects. So in this case, we're looking that, maybe one of the examples we'll have, a deck of cards, and I want to look at pulling, a certain number of cards out of that deck. How many ways can I pull, that certain number? Okay, that's what we call a permutation. Okay, and then in this case, the order matters, and I'll explain that in the example down below. Okay, so there are two things that we want to keep our eyes on, and a couple of subtleties. And the textbook isn't real explicit about these, but there are some differences without replacement. Okay, so suppose I have 12 items, and I want to pull 3 of those. Figure out the number of ways I can get a 3-piece set out of this grouping of 12 pieces. The idea without replacement means that once I pull one out, I don't put it back in. So on the first pull, I would have 12. The next one, I would have 11. The next one, I would have 10. And that would be the number of ways that this happens. We can logically kind of figure this out. Well, this is the nomenclature for the way that you formulate this. So if I have an n of 12, then that's my first number, 12. And so we had a 12 there. And then n minus 1 is 11. And then all the way down to n minus k minus 1. So we would do 12 minus 3 minus 1 would be this top number will get us to our formula. But that's the way that we can kind of start to build this. So if I do the math and do the algebra, so on this, you can see that the first item that shows up is the event number 1. It's the first pull. It's the total number of items in the pool because you could choose any one of the ones in that original pool. And then event number 2, because there's no replacement of this item, now the size of my pool has shrunk by 1. And that's why there's a minus 1 here. And then all the way down to my event k pull, that now on the kth pull, we're now at n minus k minus 1 on that particular pull. And so we can do some algebra, and I'm going to save us that part of the summary and just go ahead and give you the formula for it, that it's n factorial all over n minus k factorial. Okay? Now, compare that to the with replacement case. In this case, we start out with the same 12, right? And then on the second pull, with replacement means I pull one out, and I record it, and then I put it back in the pool, and I shuffle it again, and I pull again. So on the next one, I have a 12, and then I do this pop in the same way, and if I'm doing 3 of these, then I would have 12 chances, 12 chances, 12 chances, and I would have repeats possible in this. And so with replacement, the permutation then becomes just simply n times n times n, which is if there are k of those pulls, then it would just simply be k times n will be the way that we kind of work that. And like I said, we don't use this one a whole lot in most of the studies in this particular series, but just kind of understanding the difference that with replacement and without replacement is an assumption that you have to make or a fact that you will have to know about every problem that you look at involving a permutation. Now again, the order does matter. Okay, and that was why I underlined it up here. So the idea in this particular case is that if For us, if I say I pulled the number 1, 3, and 7 on there, and then I turned around and pulled 7, 1, and 3, or 3, 7, 1. These are considered, even though I ended up with the same 3 in the grouping at the end, this is considered the case where order matters, that this guy is different than this is different than this. Okay, so we got to be kind of mindful of that as well. And so that's what we mean when we say order matters. Okay, as opposed to order not mattering, in which case they would all be considered the same outcome. It's like I just reach in and grab 3 at one shot, and I look at what I pulled. There's that kind of approach. All right, so that's the basics. Okay, so let's try one, and we'll kind of take a look at our example. And there's the glare again. Okay, I think we're trying to get the lighting set. There we go. All right. Okay, so an example. So what we would do is we look at how many unique arrangements of 3 letters can be formed from 6 letters: A, B, C, D, E, and F. All right. So suppose you have a flashcard or a tile that you put the letter on and you throw it into a box, and we look at it that way. Okay. Now things to remember. Words on this. Unique assumes that order matters. Okay. Okay, and then we're going to assume that order matters, i.e. that ABC is different from CBA, BCA, like what we just talked about. So those are our basic thoughts. Okay, so for this particular problem, our subset is, we said we were going to pull 3 letters. So our subset is that we're going to choose 3, so 3 selected. And then N is the size of the grouping that you're pulling from. So in this case, it's 6. So all I can do is I can do a permutation of 3 out of 6, is, according to the formula, then just 6 factorial over 6 minus 3 factorial. Okay, and if you recall, the factorial symbol is that number multiplied by everything less than it down to 1, decreasing by 1. So it's 6 times 5 times 4 times 3 times 2 times 1, of course, and then 3 over then what is 3 factorial, 3 times 2 times 1. And you'll notice that these will cancel those, and I'm left with just 6 times 5 times 4. There would be 120 different groupings of letters where the order matters of 3 pulls out of A, B, C, D, E, and F. And you can sit there and go, all right, well, I got A, B, C, and I got, A, C, D, and, this would be really easy to miss one out of those 120. So this is why these permutations and the counting matter. Start to make a big deal to us. So again, when order matters, it's a permutation that we're working with. Okay, so that's our first one. All right, the other one that people tend to get confused with it is what we call a combination. And a lot of times we always talk about combinations of we use this word, and you saw me do it earlier in the video, that may have not been the exact correct, but this is the one that everybody classifies things into. But again, there are some assumptions with this guy as well. Okay, so this one is basically when choosing an unordered pair or an unordered sequence of k objects from a set of n distinct objects. So again, that's the trick, is recognizing that. So if we do it, the formula, it has some special notation. The book that we're using is a C, and then we're going to have k pulls out of n size, and they use this kind of weird nomenclature, kind of as a shorthand notation, that is kind of a parenthesis, and then they put an n and they put a k, and they're not dividing n by k. It's just these are kind of functional values that are used, and this is the nomenclature to indicate you're talking about a combination. All right, and when I do that, the formula for a combination where order matters is n factorial over n minus k factorial all over k factorial. So if you look at that first term, that's the permutation term. That's the unique number of ways. Okay, what the k factorial piece, and this kind of comes out of discrete mathematics or combinatorics, is this k factorial is a way of being able to account for repetition of components. Okay, I'm repeating those 3 things, and they can be in any order. So in effect, what I'm doing is I'm dividing that guy out. So you could calculate the permutation and then just divide by k factorial is another way of writing this guy. Okay, and so what happened is like we were saying, is that k factorial here is needed to make ABC, CBA, BAC, and so on be basically the same outcome. Okay, and again, order doesn't matter. All right, so if we go back to our pulling letters out of the 6 letters that we have. Okay, all right, there we go. All right, in how many ways can 3 letters be selected from A, B, C, D, E, F? Okay, in which the order matters. And so k equals 3, and you notice the wording was a little bit different here. And we're just saying how many ways. So in this case, I'm considering A, B, and C or CBA to be the same outcome. So again, my K is 3, my N is 6. And when I do it where order matters and I start accounting for those groupings being the same, you'll see that I've got my permutation value that we calculated as 120 before, all over K factorial. So that's 3 times 2 times 1. We now have 20 unique ways. Okay, or at the end, after I look at the letters in my hand, that I have 20 different sets of 3 letters that are happening when I do that. So you can see a combination is almost always smaller than a permutation. I guess it could be in a unique set, it could be the same, the same as a permutation value, but for us, this is, typically it's a smaller value. Okay, and so again, the note to take away from this is that in a combination that ABC, BAC, CAB, ACB, you can see I wrote all 6 of the ones that we're calling the same. Any pairing of the letters A, B, and C are all considered to be the same outcome. Okay, and so what happens is those 6 outcomes here basically are condensed or combined back into one smaller one. Okay, and this would be the outcome that has all 3 letters A, B, and C. So that's where the 6 is coming from, and that's right here is the 3 factorial. All right, so that's what we're doing with a combination. All right, so now once we've got the counting figured out and we kind of got a grasp of this combination and permutation, we can go in and we can start to we're just one small step away from being able to do probability. Okay, and if you recall, we talked about probability as just being the number of ways of a particular event over the number of possible ways. All right, so I'm going to show you a little bit of nomenclature and a little bit of writing for some different problems and show you how we start to analyze what's being said. Okay, so let's define an event X, okay, basically as being the probability of choosing any set containing A, B, C, the letters A, B, and C. And again, the wording here that you got to kind of watch out for is this says any set. And so this any that shows up here, any set, implies that order matters, okay, that we can come up with outcomes that meet this particular case. So let's define event X as being the sets of all the letters A, B, and C. And so our three sets would be ABC, BAC, CAB, so forth. You've seen these 6. These are the ones that we just talked about. But there are 6 ways that I can pull any set containing ABC. There are 6 sets of the letters A, B, and C in any order on this, okay? And so that's why it's a little confusing when we say order matters, but each one of these outcomes is a different outcome from the other. And so that's why this becomes an order matters case. Okay, the sample space then is just simply the unique 3-letter arrangements that can be taken from a pool of A, B, C, D, E, F. All right, and so once I calculate the number of ways of S, then I can calculate the probability of X as just being the number of ways of X over the number of ways of the sample space. All right, so because order matters on this, the number of ways of the sample space is that permutation 3 on 6. So that's that 120 number. Okay, the number of ways of my event X, or my number of outcomes in event X, is 6 that satisfy that criteria. So the probability of this problem of reaching into the bag and grabbing 3 letters and having A, B, C in my hand then is 6 over 120, or 1 over 20 would be my number of ways there. Okay, now this is kind of the same type of problem. Let's define an event Y then as where I pull 3 total in any order. Okay, so it's basically the same problem, but we can also analyze this in a slightly different mechanism, right? If I go through and define Y as being the unique specific event of ABC where order doesn't matter, now we're talking about a combination problem. And so set ABC is pulled basically in any order. There's only one way that I can get the ABC when I put all those groupings together, right? To get the letters A, B, and C on a pull, regardless of the order of it. So the order doesn't matter. Okay, the sample space S then, just like before, is the sets of 3 unique letters that can be made from the pool of A, B, C, D, E, F. Okay, but now this time when we do our sample space on this, because we now can say that order doesn't matter on this, okay, this now implies that we're talking about a combination. All right, so then kind of in a similar fashion, we just do the probability of Y is now the number of ways of Y all over the number of ways of the sample space. And so now I had one way for event Y over my combination of this, because again, we didn't care about the order or the grouping of those things. Okay, order doesn't matter. It becomes 1 over 20. You see that the probability of event Y is 1 over 20. And this is the exact same problem as the first one that we solved, except now we've looked at it from 2 different approaches. So you just got to kind of be mindful of the ways that you count your events in event X or event Y or whatever you're calling it, And then how you group that can also affect the number of ways of the sample space. So at the end of the day, I can get to the same answer using either the combination or the permutation to do so. Okay, now let's go look at the event, another event then, event Z, where I pull A, B, C in a specific order. Okay, A is first, then B is second, then C is third. For this example, order does matter. Okay, so our event Z is the outcome, and I put subscripts on this that A was first, A1, B2, C3. Specifically, there's only one way that that can occur. All right, okay, so then if we go in and we look at it, kind of to repeat and bring this thing down so we can kind of see stuff and have some room on here. Okay, so this is what I just wrote: A first, B second, C third, A1, B2, C3. There was only one way for that. Okay, and the order did matter. Okay, and then the sample space of this, because order now matters, it's the sets of 3 letters from pool of 6 with order mattering. This is the permutation. So the number of ways of the sample space of this guy is 120 ways. All right, so the probability of this event of getting those 3 items in that order that I want, A first, B second, C third, is the probability of Z is the number of ways of Z over the number of ways of S of our sample space is 1 way over 120 possible unique ways is the probability of pulling in order the letters A, B, and C. Okay, now if we look at our tree diagram, we kind of hinted at this a little bit earlier. Let's kind of sketch out what it is that we're looking at on this. Okay, and so what we can do then is we can look at our tree, and then we assume that this was a without replacement case, right? And so we start off with our sample space, and I list my 6 outcomes, A, B, C, D, E, and F. So this is my first poll, and these things kind of line themselves up that this would be my second, and this would be my third. And so if we're looking at event A, once I pull A out of the pool, all that's left are the letters B, C, D, E, and F. And I know it's a little light. Let's see if we can darken that up for you. C, D, E, and F. Okay, and then this, and then so on the second poll, A is now out because I didn't replace it. And so now I have a second set of B, C, D, E, and F. So there's only 5 outcomes here on this once I've come down the A path. And then so suppose I pull the B on the second, then once that's done, now both A and B are gone, and so I'm only left with C, D, E, and F. All right, and so if you look at the outcomes that occur when I start at the sample space and I follow the paths, the tree diagram, I would fill all of this out for all of the 120 different outcomes for without replacement. That is that I want path A, B, C. So I would come up to here, up to here, up to here. This would be my outcome A, B, C. If I went up to A, up to B, and came down to D, that's outcome A, B, D. And so we can start to kind of construct logically these diagrams. And what will happen in the next videos is we'll start putting probabilities on each of these legs, or start counting each of these things differently. And I can start looking at individual pieces of this diagram. And this becomes a tool for me to be able to dissect and break down problems a whole lot more easily if I can grasp the basics of what's happening there. All right, and so that's what we're saying with the without replacement case. Now compare that tree to the tree with replacement. Okay, and with replacement means that once I pull a letter, he goes back in the pool. So my sample space, just like what we had before, here's S, and now I've got A, B, C, D, E, F. This is the first pull, this is the second, this is the third. So that's second, this is third. Okay, and then once I pull A, then I put A back in, I mix it up again, and I then get those 6 to come out of that. And then suppose I wanted, on the B coming out of this, that I get the same 6. Okay, and so with replacement now my outcome is ABA for this path, ABB. This is the one that we're after, ABC, would be the unique path. But you can see that now there are a whole lot more paths that are available with the replacement case because I've got 6 times 6 times 6 using my product rule. Okay, now obviously ABA is only possible with replacement, as is ABB and a bunch of others, because I can't get that second A if I've already pulled it in a without replacement case. So you can see the tree diagram grows and it changes a lot with the replacement scenario. Okay, and if you go through and do the math on this, there are actually 6 to the third, or 216 ways, or 16 different outcomes that can happen on a with replacement problem on the same thing. So you can see that's a pretty big drastic number, right? I had 120 on the without replacement case, and I have 216 on the with replacement case. So once I do that, then I only have one path that gets me to ABC in order, With replacement, it's a 1 in 216, one way out of 216 possible that it happens. So that's a very, very small percentage probability that can happen there. All right, so that's just some ways that we can kind of start to look at counting and combinations and permutations and trying to build up these numbers without having to write out all of these sets. I like to do the sketches, just to kind of help me get my head wrapped around stuff. And I'll, generally, a lot of times I don't have room to write all of it out. But, for the first couple, I'll just kind of start mapping things and kind of looking. And it helps me to see the difference in the structures, particularly with this without replacement versus with. Because, the number of possible events in the second and the third change from what they do in this other scenario. So I want you to be kind of careful of this. Okay. In the next video, we'll get in and we'll start, we'll have some more specific counting examples that we can kind of work with, and we'll show you kind of how we can use this idea of these tree diagrams to do some very complex and interesting word problems. So if you'll tune into that one, we'll be we'll get right into it. Okay, so for now we'll end this one here. Like I say, leave me some comments down below. Let me know if this made sense to you. Like I say, this tree diagram method doesn't show up in the books very well, but I think it does a good job of kind of illustrating where the equations are coming from. And again, as I warned early on in this series, a good way to get into trouble in a probability and statistics class is to try to blindly memorize formulas. Okay, you've got to understand the assumptions and the simplifications that are being made on formulas that are presented in a textbook. That's why these diagrams kind of help me with that, and that's why I like to do them. So anyway, toss us some comments down below. If you would, like and subscribe to the video and subscribe to the channel, and we will call it a day for that one. We'll get right on the examples, so stay tuned. I'll see you in a few minutes. Okay, thanks. Bye.